Hey, so now we're going to work on a erodible channel problem. So in the problem statement, we know that the Q that we're trying to design a channel for is 7 meters cubed per second. We know that the slope that we desire is 0.0035, and we know that we're digging through stiff clay. So the first step is to determine the Manning's N value. From the right figures, Manning's N is equal to 0.025. And we want to determine the appropriate side slopes. For stiff clay, we know that a good side slope would be 1 horizontal to 1 vertical. And then we want to determine the velocity permissible through this type of channel. And so for stiff clay, we look at the figure, and we can tell that the V permissible is equal to 1.8 meters per second. That's the maximum amount of water we can pass through the channel, the maximum velocity that we can pass without the channel scouring. And then we want to consider sinuosity. Because this is a straight channel, there is none. And so the first step that we want to do is try to determine what the hydraulic radius is for this channel. And for that, we can use Manning's equation. So we know Manning's equation to be this. But we can also rearrange it in order to determine the hydraulic radius. So we know Manning's N, we know our permissible velocity, we know our slope, and because we're in SI units, K is equal to 1. And so we can calculate the hydraulic radius. And as you calculate this, you'll find that the hydraulic radius is equal to 0.66 meters. The next step is to determine what the area that we're going to have in the channel is, the cross-sectional area. And that can be done by dividing our discharge, 7 meters cubed per second, by the permissible velocity, which is 1.8 meters per second. This calculation gives us cross-sectional area in the channel of 3.9 meters squared. Next, we want to calculate the wetted perimeter, which is equal to A, the area, over the hydraulic radius. So hydraulic radius is equal to area over perimeter, and so kind of resolving the equation for wetted perimeter gives us the area over the hydraulic radius. These are two values we already have. 3.9 meters squared divided by 0.66 meters gives us a perimeter of 5.9 meters in the channel. So this next part, so we already have a value for area and perimeter, but now we want to put it in terms of the bottom width, B, and the depth of water, Y, so that we can solve for those values. So first we know that the area is equal to B plus ZY times Y. The bottom width times plus the side slope times the height, all multiplied by the height of water. We already know that value to be 3.9. Now we know the perimeter is equal to B plus 2 times the square root of 1 plus Z squared, which we've already calculated to be 5.9. So now we have a function here of two equations. Z is known because we already know that the side slope is equal to 1. So we can just replace that here. And combining equations 1 and 2, we can get this third equation. And then solve once again to get B as a function of Y. Now we can plug 3 into 2, get a function for just Y. and setting that function equal to 0, it's going to look something like this. Now something that's kind of cool about this, you look here, 3.9 was our area value, 5.9 was our p-value, and then 1.83 was our square root of 1 plus z squared. It's always going to be in this form. So if you remember that, it'll make this a lot easier. So solving this equation for y, we get that final depth is equal to 0.93 meters. And then we can plug this back into equation 3 for b and find out that our width is going to be 3.3 meters. And the last step is to determine the amount of freeboard that we want to use. Look in the appropriate figure. We can find that the freeboard height is equal to 0.75 meters. And there you have your channel design. Everything that you need. Gosh, that's like, I feel like this is so messy.